Okay, this is just going to be a really short lecture. We're just going to talk about certain things to consider when we're talking about aqueous equilibrium, specifically with KSP and solubility, the molar solubility constant versus molar solubility. So first and foremost, how do we know how to predict what's going to be more soluble in acidic solutions? So there's a couple different things we can look at. The first thing is the anion. If the anion is an anion of a weak acid, that means the conjugate base is going to be strong. Okay, so if the conjugate base is strong, then it'll be more soluble in acidic solutions. So for example, if we have barium fluoride, the fluoride ion, when it dissociates into its ionic form, that is the anion of a weak acid, hydrofluoric acid. So if it's the anion of a weak acid, hydrofluoric acid, then the anion itself, oh, that's a bad circle, sorry, will be a weak-ish, we'll call it a weak base because it's not a strong base, or none of these are strong bases or strong acids, but it's going to be stronger as a base than the weak acid HF. So the fluoride ion is a weak base and will be more soluble in an acidic solution. An anion that's the anion of a strong acid will be pH neutral. Okay, the anion of a strong acid, when it dissociates, is pH neutral. Remember all those times we've done those problems and you're like, why are you ignoring the chloride? Well, chloride ion is the conjugate of a strong acid, hydrochloric acid. It's pH neutral. It doesn't affect the pH. Iodide ion is also another one. It is the conjugate of hydroiodic acid, which is a strong acid. So that ion, that I minus, is pH neutral. Therefore, it's not very soluble in acidic solutions, which also should make sense because we're talking about strong acids and it is acidic. So the conjugate is pH neutral, can't really do much, so it won't be very soluble. If the anion is a hydroxide, it's a strong base. Sodium hydroxide, magnesium hydroxide, calcium hydroxide, etc. Strong bases are very soluble in acidic solutions. Some other examples are the sulfide anion and the carbonate. These are also very strong bases in solution. So if you see that hydroxide, sulfide ion, or carbonate anion, then you know you're going to have something that's very soluble in acid because it's a very strong base. Now, how can we compare the solubility product constant and Q? How do we compare those? Remember, K, generally speaking, is at equilibrium. Q is at any other point in the reaction. So if Q is less than KSP, the solution is going to be unsaturated, meaning more solid can go into the solution and it'll shift right. More of that solid will be dissolved. If Q is equal to KSP, it is completely saturated. No more solid can be dissolved into the solution. If Q is greater than KSP, it's a supersaturated solution, and the dissolved product will now precipitate out of the solution because no more can be held. So here's an example. If I had 0.01 molar silver nitrate and I added to it 0.015 molar potassium iodide, I am telling you, because I've looked on a chart, that the KSP for silver iodide is 8.51 times 10 to the minus 17. So what's going on here? Is this very soluble? Will anything precipitate out? Can more be added? Well, we're going to compare Q and KSP. Now, if we write the balanced chemical equation, which is always the first thing we should do, balanced chemical equation, I've gotten this just from solubility rules. I see that silver iodide, based on solubility rules, is my product. Okay, it is a solid. Halogens are generically soluble unless they are bonded to a silver, mercury, or lead. So in order to solve for my Q, I'm going to take my silver ion, my iodide ion, plug in their values, and get a Q of 1.5 times 10 to the minus 4. In this case, this is significantly larger than the KSP. So if Q is significantly larger than the KSP, we should see the silver iodide precipitate out in the new mixed solution. With complex ion equilibria, the only thing I'm really going to have you guys worry about is the formation constant, yet again another K, and it's the same as all the other Ks we've done, products over reactants. So if, for example, I had this reaction here, silver ion plus 2NH3 yields silver ammonium, and that formation constant is 1.7 times 10 to the 7. Well, I can set it up like this, products over reactants, and that's just one way I can manipulate the formation constant. So the constant in which the product is formed. That's it for this lecture. Really sweet and short. I am going to put some other lectures up that have to do with the next chapter. The next chapter we're doing is thermochemistry. I will put that up in the next day or so. If you have any questions, feel free to email me.